project development in a lot of functional languages. In particular, we have a couple of pretty significant Clojure projects. Everything else, I believe, has been said, so let's get right to it. I first want to, so in a former life, I did a lot of work with Scheme, which I think you all know has close relationships with Clojure. And I was a project editor of the 6th edition of the standard of that programming language. And out of the work on Scheme grew a lot of work on teaching beginners on how to program, in particular, usually at the university level. So there's still a web page called dyneprogram.de where there's a lot of material from that. And we closely cooperated with the Program by Design program in the US, which is significantly larger and which pioneered a lot of the stuff that we did with dyneprogram. And I want to tell you how some of that, how some of the insights we gained in those projects can be applied in Clojure. But first of all, does anybody know who this man is? You should. This man is Bob Harper, and he's one of the smartest people in programming languages. In particular, he's firmly in the camp of typed programming languages. And if you read his blog, you will find out that you all are firmly in the camp of untyped functional programming, right? Now, of course, you're in that camp for a reason, right? And I want to talk a little bit about those reasons. But I think untyped is something that poorly characterizes what we do in day-to-day programming in Clojure or in Scheme or in any of those other languages that are not statically typed. And I think a better term is latent typing, where we emphasize the fact that we do have types, but those types are attached to values at runtime rather than to expressions and variables at compile time. So the latent refers to the fact that it happens later in the program's life cycle. But I want to keep you in mind that latent typing is about attaching types to values. And you know, the word type does occur in Clojure as well, and you can define types in Clojure. And in fact, if you want to know how you define a type in Clojure, what you need to do, you can look on the internet, and you will find a very nice chart by Ches Emmerich that shows you exactly what you need to do if you want to define a type in Clojure, which is the upper left corner. But does anybody think this looks a little complicated for this pretty simple sounding question, maybe? So I'll get back to that. Not all of it, so don't worry. So really, so what's nice about that chart is that it tries to be systematic, right? It tries to give you a recipe that you can follow that will give you a definite result on what you need to do. So that's really what I want to talk about. So I want to talk about systematic software development, and that is really what we focused on when we taught beginners on programming, or even when we do that to professionals who want to learn functional programming coming from a different background. So systematic really means that there is a system in place, that you're methodical about things. And when you teach beginners on how to program, it's really valuable to put that system in words and not just give sort of little little proverbs and little helps and little strategies, but really verbalize what you're trying to do. So dyneprogram and also Program by Design focus on something called design recipes. And what they say is, well, whenever you design a piece of functionality, you should always follow the same sequence of steps. Don't worry, I'm not going to, this is just so you know that there is a sequence of steps. And today I want to particularly focus on data analysis. I'll talk a little bit about some of the other aspects there as well. As a professional programmer, you might think, I'm a professional, I've done this for many years, I don't need no stinking steps, but it really helps beginners, and I think it also helps professionals. So I'll illustrate that using a classic example that we often use in many different contexts called geometric shapes. This is a small portion of a classic problem posed by the US Navy on what's called a geometric region server, which is about the spheres of influence of Navy ships at sea. And here's the important part of the problem statement. It says, well, a geometric shape is one of the following. It's a square, a circle, or overlay of two geometric shapes. And all this happens in the two-dimensional plane. So somebody always asks me, can that square be like this? No, it's parallel to the axis. It's not. It's supposed to be a very simple problem. And here's the problem statement. You can pose that problem in any programming language. It can be done in any language you want. And it says, well, implement geometric shapes, design a representation, and write a program that will figure out whether a given point is inside or outside a geometric shape. And so the data analysis step of the design recipe says, well, you start by looking at the interesting nouns in your problem statement. And the interesting nouns in this case, well, it's about geometric shapes, so I'm just going to say shape from now on. There are squares, there are circles, there are overlays, there are points, and there's sort of the two-dimensional plane as well, but that plane is sort of the atmosphere in which everything happens, so we don't need to represent it explicitly. Those nouns have a little bit of structure in that, well, there's this word shape, but it really encompasses 3 different classes of shape. There's squares and circles and overlays. And one of the interesting questions is then how does that diagram translate into your programming language? What we call it in program by design and dyn program is we call it mixed data, because sort of in a place where a shape can occur, you have circles and squares and overlays all mixed together. You might know this as a sum type or as a discriminated union or something like that. The word doesn't matter, but I think you can all relate to that concept, right? And that concept can be identified usually when you can use this wording, when you can say, this is one of the following, right? And it's important that it's one of those things, and also that when it is one of those things, you can tell which one it is, right? So you don't have those things where you're not sure, is it a square or a circle? No, you always know. So that's one way to structure data in a systematic manner, is to think, is it mixed data? And of course, well, the categorical dual of this is composite data, which is when you have something that consists of multiple parts or that has multiple attributes. So you might say a circle has a center and a radius. So whenever you have wording that is like it has, and then come a bunch of properties, or you have like consists of, a whole consists of several parts, then you are dealing with composite data. And the design recipe then gives you explicit instructions how to turn that data analysis into code. And I'm going to show you how that's done within the teaching languages that we developed for those programs. And this is the actual wording. The wording is not particularly interesting for this talk, but you should know that there is wording. And what it says is, well, first thing you should do is you should translate the results of your data analysis into sort of a structured comment. In this case, for composite data, where you use that wording, it consists of, or it has, and then you identify the fields, you identify how many fields you have, and you give what we call signatures to things, which is just a name that you can use in your program that sort of corresponds to a type. So in our case, and then when you've done that, when you've written that structured comment, you translate it into what is in the teaching language is a record type definition. And that looks like this. So it says define record procedures, which is a keyword. Then you give that thing that you're naming, you give it a name, the signature. You give the names to the constructor, a predicate, and a bunch of selectors or getter functions. I'm going to just show you an example. I think that's going to make it clearer. So a circle, for example, consists of these 2 things. It has a center and it has a radius. And so we define record procedures associated with the signature circle. Then we are going to name the constructor called makeCircle, which we can use to create circle objects. There's a circle predicate, which distinguishes circle objects from other objects. And then we have 2 selectors or getter functions corresponding to the fields of the record. So there's circle center and circle radius. Is that reasonably clear? You all do parentheses? OK. Great. Also, and I think that's going to hopefully going to make it even clearer, is you can write what we call signatures. And they look like type signatures, but in the teaching languages, those are checked dynamically. And they sort of illustrate what those magic functions do that have been defined by this define record procedures form. So for example, the constructor accepts arguments corresponding to the fields of the record, right? You have these signatures 1 to n corresponding to the fields, and it produces something of the signature of the record itself. The predicate, well, it accepts any object, and it will give you a Boolean telling you whether it's an object of that particular type or not. And each of the selectors takes an object, of our record type, and it produces an object of the type of the corresponding field. Right? Does that make sense? OK, nod. Everybody nod? Good. So, and you can, here's the whole thing. Here's a bunch of signatures. So it says make circle, takes a point and a real corresponding to the center and the radius, produces a circle. Circle P goes from any to Boolean. And the selectors, of course, it's kind of redundant, but it's useful to write it down when you're starting to learn how to program. Both of those accept a circle and then produce either the radius or the center component of that circle. And, well, you can see how that goes on, right? You might have a square characterized or consisting of a lower left corner and the length of the edges of the square. But I think you'll see that then putting the design recipe into action will produce something that has the exact same structure as for circles, which also has two fields. Okay? So there's no surprise there, square, except that the two fields are called corner and size, and the whole thing is called square. Now, you remember these were all different classes of shapes, right? There were circles, there were squares, and now there's overlays. And overlays start off also as just being standard composite data. We said that's an overlay consisting of two shapes. But there's an additional element here in that it says, well, an overlay consists of a geometric shape and another geometric shape. And geometric shape is sort of the type that we're in the middle of defining, right? So there's a self-reference here, which is not relevant for the data representation of overlays, but it will be relevant when we write functions that operate on that representation. So overlays, as far as the data definition and the record definition are concerned, again, are basically the same thing as circles and squares, only that the whole thing is called an overlay and that we have a top shape and a bottom shape. And if you remember the list of nouns that we had in the beginning, it also mentioned points. And now it gets really boring because points have x and y coordinates, so they also have two parts. And you get, again, a record definition of the exact same structure that we've already seen 3 times now. Now, I showed you in the beginning, or I said, well, we can translate those data definitions into code, and I showed you how to do this with composite data. In our teaching languages, there's also a way to convert data definition for mixed data into code, where you're essentially interested in the signature. So you can say, well, a shape is a signature where we have mixed together circles and squares and overlays, right? So that makes it very explicit what a shape is. And then, once you've got all that in place, your data definitions and your and the corresponding code for the representation, you can start writing functions. And you remember the problem was finding out whether a given point was inside or outside of a given geometric shape. And and the design recipe said, well, first of all, you start writing a short description, which is enough to write a single sentence or a single line, and then you write a signature. And the signature includes a name for that function that you're writing. So in this case, we want to know whether a given point is in a given shape. So that function must accept a point and a shape and produce a Boolean that says, yes, it's inside, or no, it's not inside. And if you look at the signature, you can see that you can already write down some parts of the function definition, right? I hope, def, define, think def, right? Lambda, think but it's pretty close to Clojure code, I think. And so we know that our function is going to have a define in it, that we're going to mention the name of the function again, that there's going to be a lambda, and that also we're going to have 2 arguments, and that we'll need parameters corresponding to those arguments. In this case, it's just p for the point and s for the shape. But we can do more because we know the structure of the signatures mentioned in the signature for the function. We know that we're dealing with points, which are composite data, and we know we're dealing with shapes, which are mixed data. So there's a couple of things we can write down in our function, what we call the function skeleton. In particular, with composite data, so the point is composite data, there's not much you can do with composite data except take it apart and look at its parts, right? Unless you're just passing them on somewhere else. So when you're dealing with composite data, it's usually a good idea to just write down applications of the selectors, of the getter functions, in this case, where you look at the x and the y coordinate of the point, okay? So and these dots just mean, we don't know yet what that function is going to look at in the end, but it probably will contain applications of the getter functions. And with mixed data, there's not much you can do with mixed data because you know there's these different things mixed together, and in order to do anything useful, you need to find out which one of those things, which one of those classes your object belongs to. So you're going to need a cond that just uses the predicates to identify whether you're dealing with a circle, a square, or an overlay. Does that make sense? Okay, so you just write it down, and you know, if by this time you might notice that we're just using the information from the signature. We're not thinking about the problem at hand, or we don't need to think about the problem at hand. This is purely mechanical. And we can do even more mechanically because we know circles are composite data, squares are composite data, overlays are composite data, so we can write down the corresponding applications of the selectors. And moreover, we know that overlays contain self-references. And when you're writing a function on data with self-references, it is most of the time for a recursive call. And once you've written all of that down, then it is time to think about the actual problem statement again. You know, it's not particularly exciting, but you might notice that for the recursive calls, if you look at them, you can see what question they answer, right? The first recursive call answers the question, you know, is my point in the top shape? And the other one answers the question, is it in the bottom shape? And once we sort of think about it in those terms, it's pretty easy to combine the results to answer the question, you know, point and shape of P and S. So the complete definition then results like this. So I've shortened that process a little bit, but you can see the idea is that you would proceed in a mechanical or systematic manner as far as possible. And once you've done that, then you apply your domain knowledge to fill in sort of the missing parts, the ellipses in your function definition. And by the time students get to this point, it's usually pretty easy. And hopefully following along, you might have gotten the impression that this problem is pretty easy to solve. It is very easy to solve using this approach, but I've seen many professional programmers and educators completely fail at this. So, I mean, not being able to solve the problem at all, right? People will get this idea of, you know, getting spline representations and whatever, you know, in a job interview. I don't know. So just so that you know, so you might have fun just giving that problem to someone you know who wasn't here and see how they do with it. So anyway, so I showed you how to do this in those funky teaching languages, in this antiquated Lisp dialect scheme. So you might think, well, we could do this in Clojure, right? No problem. Clojure has record definitions, and we can translate those record type definitions into def records. And look, you know, they're much more concise than the ones, you know, than this all that stupid verbosity in those teaching languages, you know, which is fine for students. They have a lot of time, but we can do this here. And you can see, well, you can easily see that they sort of give you the same structure and the same ideas that you had in that code in the teaching languages. And of course, you can then write a function definition. I haven't done the whole thing yet. Just so we can focus on the important bits. But you can see that that function essentially looks pretty much the same as the function in the teaching languages. You know, there's a short description. Unfortunately, Clojure doesn't have a signature language, but it's easy to imagine what that might look like. But I want to direct your attention to those things here, right? You know, what's a selector? You remember in the teaching languages, you had to write down the name of the selector, and you don't have to do that with Clojure defrecord. And instead, what you use is you write :radius. So when you come from those teaching languages, you might say, okay, I just need to remember that the selector function is called :radius to extract the radius from a circle object. But you probably know that that's not true because :radius is just a keyword, right? And what we're really doing is we're doing a map lookup on that record, which will give us the value of the corresponding field. And you might think, how neat, right? I just need to remember this one thing for using maps and for using records. It's the same thing. Unfortunately, that is true until you make a little typo, right? So, you know, you're in the wrong country, and you write this other thing, right? And you know the first expression is going to get you the center, you know, the point object that is the center of the circle. Does everybody know what the second expression will give us? Will it give us an error? It will just give us nil, right? And a lot of Clojure functions just will willingly accept nil and accept it as the empty list or the empty map or the whatnot. So the error from this will propagate through your program. And it might run for quite a while until anything, you get a message or anything fails, or it might not happen at all. So you can actually work around this because defrecord also defines getter methods for the records that you can use. So you can sort of treat them as Java objects. And so you can write .center of C1. And the neat thing is if you use that notation and you make a little mistake, then you will get an error message at compile time, which is really nice, right? And so you might think, well, I'm just going to do that. Unfortunately, that first expression, well, I made a check mark there, but what it really gives you is this. You get a reflection warning, and in order to get rid of the reflection warning, you need to put type annotations, which are annoying. And which don't really buy you anything in this context, right? And this is in this program, right? In the space of like a single line, between two lines, the Clojure compiler has forgotten the type of C1, right? And it goes further. This analogy with maps goes further. So for example, you can use assoc to do sort of a functional update on your objects. And it's all well when you don't make a mistake. But when you do make a mistake, that record that you had suddenly acquires fields or map entries that the record type definition didn't have. And that error can propagate even further in your program without you getting an error message. And I don't know if any of you have ever tried to rename in a larger program, the name of a record field that is shared with other record, or anyway. So we eventually broke down and developed a little library called ActiveClojure, which is somewhere on GitHub, and gave ourselves, or I forced everybody to use a record type definition that corresponds to the one that in the teaching languages that we define. So you define the type name, you define the constructor name, you say what the arguments of the constructor are, you define the predicate, and you give explicit names to the selectors. And those selectors will only accept circle objects. If you give them anything but a circle object, they will give you an error message. And we found that this, we like this better. So, so that's sort of the gist of this talk. So I'll rant a little bit more about sort of the use of unsystematic programming in Clojure. So this diagram, so I was wondering, well, if a def record is there, right, does this diagram somehow correspond to my suggestions for you using def record? And in fact, so there's just a bunch of questions. It says, will the type need to extend Java class or implement any interfaces? No. Will the type participate in Clojure protocols or be associated with performance-sensitive code? And if the answer is no, you're supposed to use a regular map. And I think that's a bad idea, right, obviously. And then it says, is your class, and if in order to get here, you need to answer another question, the positive, which is your class modeling a domain value, thus benefiting from hash map-like functionality and semantics? And to be honest, I have no idea what that means. This is in a lot of places in the Clojure community, right? So, there's a Stack Overflow question, says why ring requests maps instead of records? And Weave Jester, the author of Ring, said, well, the Ring spec was written before records and types, so I can buy that. But then he says, well, records aren't that much faster. And really, the only real advantage records have is polymorphism and something else that, again, I didn't understand. And so Falco is here. I saw a really nice tweet, right? So there's big tooling around this problem, right? You can install another component that will then validate your maps. But really, in a lot of places, you shouldn't have used maps in the first place. And then you don't necessarily need. So schema is great, but you should apply to situations where you have maps. And a lot of places maps occur, you really should have used records. So in case you're wondering, composite data. When you're dealing with composite data of arbitrary size, then it's appropriate to use collections such as maps and sequences and whatnot. And if you have fixed components, if you can say, my thing always consists of these 5 parts, use records. Don't use maps. This problem sort of spreads in Clojure. I don't know if you're wondering if there's something wrong with the exception mechanism in Clojure, where the dispatch is based on types, but there's only one way to construct an exception, and you can't attach a type, and it's really, really cumbersome to define a new exception type in Clojure. And so we broke down, and I put another little library in ActiveClojure that gives you sort of a type mechanism for conditions that are composable. that are based on what I did for the scheme standard. And there's a lot of other things that maybe you can help me with. I have no idea. So if you look at the standard data types in the standard Clojure library, there's a lot of sort of little gaps that are, and little additions that I can't understand. So maybe somebody can explain to me why there's next and rest, for example, which are, which goes very deep. There's no seek predicate. Why is the seek always used as a terminating condition? There's a, huh?
There is seek predicate.
Really? It is now? Really? Does it do what I want? I want to know if I can call first and rest on it.
Yes, it does.
Oh, really? Then thank you. Then, I'm already happy being here. But list star is this function that gives you something that is not a list. I don't know if you've noticed. Conj, I can see why it sometimes needs to add at the beginning or the end, but because it's essentially supposed to be a method on collections. But you can also apply it to nil, right? And it will not bomb out. It will give you a sequence, but you might wonder which type. And then there's types which have no constructor in the Clojure ecosystem, such as key-value pairs and maps. They exist. You can extract them. They have a type. And you can construct them, but there's no constructor. So let me sort of conclude with this. So don't get me started on duck typing. Instead, be systematic, type your data, read our blog, come to BobConf next year. Thank you.